Hey, how's everyone doing today? Good to see you here, Max, Kenneth, Matthew, Matthew, good to see you here, Kevin, good to see you here, Bond, good to see you here, Wilton, good to see you here, Emily, good to see you here, Kevin, good to see you here, Reed, good to see you here, Lillian, good to see you here, Nathan, Clayton, Max, Anna, Nathan. How is everyone doing today? I gotta say, the biggest thing, I wanna point this out, is once again, Lindsay, good to see you here. You know what? I'm doing it. Tell people if they are not here. Brian goes crazy with those points. Hashtag show up. Make sure you are here to practice and review. Who's been working on the assignment? Feel free to swing by today's office hours. They are the last office hours of the week, and we're going to do some activity later today. So I'll send out an announcement about the activity. I'm going to do it after the classes. My brain's a little bit fried after all the classes. So Brian's a little bit burnt out from coding all day. That's where I might be a little bit slower with my coding. But the biggest thing is show up, get these points. I know, Nathan, right? Hashtag show up. That's what it's all about. Keep getting those points. Keep showing up. Keep being here to practice. I'm trying to start the material quicker because I looked at the analytics. And the analytics show a lot of people skip this part where we're talking about the important stuff about staying on track and doing well, which is important. And I got really sad. I don't know. I looked at the analytics and it's like, people are not watching this portion. So I'm like, let's focus in on getting more work done. So last class, we finished up correlation. We're going to put the activity out for later. So we're actually going to start. Oh my gosh. No way. Today will be such an amazing day. Because anyone know the name of the class you're in? Does anyone know the name of the class you are in? Who knows the name? Like, you'd be like, what class am I taking? Where am I at? What's going on? Where am I? Do I even exist? I am in BAS 320 regression modeling. That's what you're in. You're in BAS 320 regression modeling. Whose trade just happened? Oh no! Is it in our league? Don't do that to me. I'm doing all right-ish in our league. I'm doing my family league. Doing all right, 50-50 my family league. Lucked out last week in our league. I'll take that. You're in regression modeling, so guess what? You know, it might be a good idea if we went over here today. We didn't do slides yesterday. That's why. Hey, if we started talking about some regression modeling. So this is really good. I wish I got some 201 students who are just on fire right now. I saw your name and just signed up. Well, thank you, Walker. I appreciate that. That's very kind of you. Everyone's been so nice to me. It's been a big week. A little stressful on Tuesday. Everything got worked out perfectly fine. And last night was the Stats 101 test. And some classes had some assignments due. So I was replying to a lot of emails, a lot of messages. And then we didn't have one thing set for Proctorio, but it all worked out. It was fine. But busy nights. But I like to be busy. I'd be bored if I wasn't busy. Why be bored? But today we're doing regression, and what's the point of regression? What's the deal with regression? So why are we doing regression? What is regression? And why do we go from doing correlation to a 1? I wish you were here to hear this. Why do we go from doing correlation to then talking about regression? Why are we going from correlation to regression? What's the point of it all? Why would we go from correlation to regression? So think about like why these chapters connect. Because I said so. I'll take that answer. It's true. I do say we are doing this. They are related. Nathan right there, some great answers too. Keep getting those points. Relationship between two variables, but only between. Wilton, good answer right there. Great answer. I just wrote down why not a little more points. Only between two what variables? Regression is the idea of fitting the line. So I've drawn a regression line on there. And correlation is the relationship between two quantitative variables. So you can see here the correlation. And when we talk about regression, we're talking about fitting a regression line. So the regression line itself is only going to be used for linear relationships. Important right there. We're going to look at right there because regression uses and we can go into multiple regression. Association so regression is just a specific, Daniel, great answers right there. Regression is just a specific type of association. Generally, when we talk about linear regression, we're talking about two quantitative variables. There'll be other types of regression. So when we say simple linear regression, we can break this down a little bit more. Simple means 1x right here. So this is 1x. And then the line part of it, the linear means, you guess it, a line. And the regression basically means an equation of sorts. So we're doing so it's like, this is the equation of it. So simple 1x, making a line with it, and regressing two variables to make an equation to simply do something like, everyone knows this. I mean, come on, say it with me. Y hat equals B0 plus B1 X1. Exactly what you're going to say, right? Put that thing in the chat that Brian hates. Do it. Put that bad thing in the chat. Do it. Uh-oh. Put that thing we don't want to see. It's not the end of the world if you remember it. You probably didn't say B0 plus B1 X1. You probably said Y equals... What did you probably say? I bet you were saying when we talked about that line right there, you said Y equals MX plus B. Emily, right there, some points. You probably said Y equals MX plus B. You were taught that. Someone taught you wrong. Algebra person taught you wrong. So Y equals MX plus B, it's the same deal right here with the same sort of components. If you look at how it, if you just focus in on it, you'll see B0 is the intercept and B1 is the coefficient of the X1. And I do want to mention this. We're actually doing a quick overview of what we're doing here. This is a good overview of regression. Why I like this equation better is I want you to go out on a limb and think, when we get to multiple regression, what would Brian add to this equation if he had a second X with a second coefficient? No, wait. Dang. Wait, did she teach you the right one? So if we were to have a second X with a second coefficient, what could we add using this sort of notation right here? Which is really the greatness of it, I think. If you had a second X with a second coefficient, so here's a hint. Here's the first X with the first coefficient, and I could just go here. Exactly. And then when we get to multiple regression, we'll just go B2, X2, and then that's the second X with the coefficient of the second X, which is just a second variable. Great job right there, 50 points following along. So you actually just learned a little bit of multiple regression. It's exactly, that gave out the points, but button didn't work. So that's using multiple regression right there. Excellent work. Make sure the buttons are still working. Good job. And so we can understand what we're doing right here. All the good stuff. Motivation philosophy right here. What are we talking about? We're talking about an association. Now, as we said, regression is going to build a what for us. The whole point of building a regression is to make a what for a line. The whole point of doing regression is we have some sort of X and some sort of Y, and we are going to make a what right here, a line, and that line is going to allow us to make what's. That line, I'm going to draw it in blue, is simply an equation. Great job right there following along. That is an equation. It's just a mathematical equation called the line of best fit, and it's the line that best fits through the data. And what do we mean by best fit? Well, here, I'll draw a line of bad fit. A line of bad fit could look something like that. That's a pretty bad fitting line. We'll understand more later on as we go through how it has the largest reduction in the sums of squared error, and that's why we call it the line of best fit. It's the one that reduces the sums of squared error the most. More on that later on, but we call it the line of best fit through the data. So when we have this equation right here, we can use it to make prediction for new individuals. Like we could say, you know, we don't have much data in this range right here. What if we had a data point right here, like right here, what would we predict its Y value to be? Or we could use this line to describe what's going on. This is the difference between predictive analytics or descriptive analytics. And just imagine this. If you're working for like a baseball team, you might say, okay, if we were to get someone swinging the bat this fast, what would be their batting average? Because maybe there's a big, or their home runs they hit, because how fast you like get the bat going when you swing is like a big thing in baseball. Please tell me, I'm not wearing sports today. Tell me if I'm getting the sports stuff wrong, but I think you want to get that bat to go around pretty quickly. That's like the whole goal is like you come in, you swing, and the bat goes whoom and just like zooms around. So we would expect, or the model shows that, and this is the descriptive part of it, we can describe that players that have a faster bat speed are hitting on average more home runs. So we have home runs over on the y-axis, like home runs over here, and then we have bat speed on the bottom right here, bat speed, Brian Stevens right there. Bat speed on the bottom, we see that higher bat speeds, and this is the descriptive part of it, players with higher bat speeds tend to have higher home runs. Now, you can't say for certain, that a player with this bat speed that we've drawn out right here would get this many home runs, but the model what's this? The model what's for this player? For this player right here, who would have a bat speed of this, the model would what home runs for them? Suggests or predicts or expects. Be very careful. We don't want to say they will get this. Will is a very bad word to use in predictive analytics. It implies certainty. 50 points following along right there. We don't want to say words like they will get this many home runs. Be like, oh, if we get the player to this bat speed, they will get this many home runs. No, no, no. We would expect them to get more home runs. The model suggests players at this bat speed generally observe on average this many home runs. And that's what the line actually is. It's actually an average of what we would rip to anyone named Max got the jokes in the chat. Who's got the jokes? Max got the jokes. So when we do a regression right here, anytime we do a regression, it must be between what? There's a lot on this slide, but it's just one concept. Anytime we do a regression, linear regression, I should say, linear regression must be between what? Linear regression must be between what? All of these you see right here. How much a movie would make based on its opening weekend. So if we have here right here, how much a movie makes, actually that would be the Y, because we want to know how much the movie will make total. And based on its opening weekend, what are the sales from Wednesday to Thursday based on 600 customers right there. So we're trying to understand sales. How many units of a new product expected sold in week 25? That's what we want to understand based on week 15. That's an X. How much is the household income? That's the Y of interest based on this right here. Not a 0 and 1. Sorry, Will. 20 points to Will right there in the chat. 2 quantitative variables. These are all 2 quantitative variables. If someone graduates with high school with a GPA of this, and look right here, now we have multiple, any plays in the band. Ooh, gonna have an issue right here with this later on. That's a categorical variable. This is for a later chapter. But basic regression, basic, simple, linear regression. We'll have a trick for this later on. We can actually make that quantitative. We'll do a trick right here. Not today. We'll not be working with this one today, but we could find a trick to make this quantitative. There's a trick for that. That is categorical. If you play in the band, that is categorical. We want to predict someone's GPA. Not today's topic on how to turn that categorical, though. Someone's GPA right here would be, their college GPA would be the variable of interest. Now, if you notice right here, the Y variable is always the one we want to what? The Y variable, called the variable of interest, or the response, is always the thing we want to what? Put your own words right here. If you're wondering, well, which one is the X and which one is the Y? Whenever you're doing equations, your Y variable will be the one you want to what? Predict, understand, make a model to know. Like, we want to know, why are people getting home runs? Just say, why do people get home runs? Maybe bat speed explains it. Why do people have good college GPAs? Maybe it's their high school GPA. Maybe if they're in the band, maybe it's their ACT score. The X's explain why something is happening. So important to know where things go on the equation. I hate the words independent, dependent. We don't do that here. So I just like to say X's explain why something is happening and the Y's of interest. You work for a company, you're probably interested in your what. Take a look at the screen right here and tell me, if you work for a company, you're probably interested in your what at that company. You'd say, I want to know my this if I were to go to a company. You're going to go work for a company, you say, I might want to know. Megan right there knows what's going on. X explains why something happens. The salary of the company. You might want to know your salary, making it the Y variable of interest. Maybe it's your education that explains it. Maybe it's your experience. Maybe it's your months on the job. Now, these are all 3 simple linear regressions. Review question. I'm throwing 100 points on track today. I want to say this. Everyone who's following along right now, you're doing an amazing job, and I'm really so proud. Sometimes I get my energy when people follow along, and you're giving me so much energy right now. Why are these all 3 simple linear regressions? Why are these all three simple linear regressions? Because each one of these is an equation created from what? Why are these all 3 simple linear? This is 3 separate simple linear regressions. You got it exactly right there, Matthew. Great job, Matthew. Worth those 100 points. It's all 1x. It's just 1x, 1y, 1x, 1y, 1x, 1y. And then we are just dealing with quantitative today. Do remember QQ straight enough, no outliers come to play right here. So once again, I showed you the equation, but you say, Brian, that's not what you showed us. You showed us something a little bit different. You showed us, It's way later on the notes. You showed us. Oh my gosh. That's the equation. We're ever going to see the equation I like? Bueller. Bueller, Bueller, Bueller. That's about it. I never write my equation with the truth. I've hit the sad music so much today. I don't like that equation. Whitson, let's put that in the jokes right here. Whitson's cracking me up the chat. I swear it's in the notes. Extra quotes right here, Whitson. Jokes from Ubot. Okay, so what's the difference between these equations? So here's the equation I like. I'll explain why. Is it only in the multiple regression? This is sample statistics. I prefer this because we never deal with the truth, because in statistics, we're dealing with samples. But if we knew everything, which is what we want to understand, which is the whole goal of inferential statistics, to understand a population. So if we had a population, then a population would be written the true mean. Remember how I said that the line is an average? The true mean of y given some x. So that's just saying if we are at some point right here, then at some point x, this line up here is the mean. And it should be the mean of the points. You see how the dots around it? That line, let me draw it in blue. That line should be the what of those y points. The line should be going through at any given x point. Like if I drew another given x, like I only take at some given x, then the line itself should be a what for those, should be the what for the y at a given x. Like here's at x1 and here's at x2, like a given value of x. At a given value of x, the line will be a what? And does that make sense visually right there? Like that is saying the mean of y given some x. And so the line right here, which you see, we are trying to say that we are trying to understand for a population that this line is an average of the x values at that given y. So we're not saying it is the value we will observe. It's saying on average we would observe this over time for multiple trials at a given x period. Good theory stuff right there. And that's why this equation is good. So what we put right here is not the estimate of the intercept, is we put right here beta, which is the true, and that's my B's right there, because I'm Brian Stevens. So that's the true intercept. I'm told I write my B's very weird. Thank you, kindergarten teacher. We had to learn cursive. And so now we go here to B1, beta 1, excuse me, and that's X1. So the small differences you're seeing right here is this is Greek notation. The mean at X. Exactly. And so the Greek notation right here differs from the sample statistics because we have right here the true mean of y, which is mu, given some x, is equal to the true intercept plus the true slope. And then we often add on here, if there is a miss, some disturbance, some epsilon disturbance. We will not be using this much in practice because in practice, do you have all the data, yes or no? Do we need the other one? I guess you could call it a mean x. I like the first one better. I think we'll throw width system points there. You don't have all the data in the practice. Fancy B's. I write a lot of B's, capital B's, in cursive. So you do not have all the data in practice. In practice, when you do statistics, you are dealing with samples. And if you took my Stat 1 class, you probably remember SSPP is that sample statistics are going to give us inferences into population parameters. So a sample statistic is an inference into a population parameter. So whenever we write these equations, we're most likely using these sample statistics created from a sample that we have to estimate the truth for population parameters, which is going to be one of the key things right here. Does everyone understand what these components are? And we'll be seeing this visually in a second right here. I'm going to circle a component and I want you to tell me, Brian, that is the this. And I'll give you hints. What is this right here? What example of what we would use a population? We generally don't. If you had all the data, And then you would say you know the answers. Megan, that's a really good question. We generally don't have the population because then we're not doing statistics. We just say, here's the answers. Here's all the data. And rarely do you ever have all the data because theoretically, a lot of times, like if you're looking at baseball players, it's a sample of baseball players who are like in the major leagues. So theoretically, there could be more players, less players over different time intervals. And if a player plays a game, that's like a sample of them playing a game because they can play infinite games. So you can't say even all the data in the major leagues is just samples of what players can do. Like every time a player plays a game, they're sampling their abilities. So you would say, what do we expect from this player from what they've done in the past? There's going to be more observations in the future. So you'll never have all the data on what baseball players do. You'll just have samples of what they do. Because every time they play a game, it's just a sample. It's just like, yeah. So like you could say for all the games that have happened, but probably we want to then estimate what could happen. So statistics is oftentimes not about observing all the data and coming up with the answers, but observing from a sample. Yeah, so no, that's why I don't like this one. That's why, because it's the theory behind what we're doing. I'm not a big fan of theory, especially when I played music, which I should have probably been a bigger fan of. It's the theory behind what we're doing is we're trying to make guesses about the truth for everything. Does that make sense? So this right here is our best guess of the what. Like from a sample, we would have a guess of the what, and I'll give you a hint. That right there is our best guess of what. It's our best guess of the truth for the population, and that is our sample what. And I've drawn a hint up top with the color. So that is our best guess at the true what. So we're saying, okay, let's take a sample, and then this is our best guess at the true this. This is an equation we wish we knew. The population parameter, and that is the population parameter for the what of the line. You are correct. That is the population parameter. And excellent words right there, remembering population parameter, which is just a quantity for the population that we're trying to understand. So that is our best guess of the y-intercept. Exactly right there, the intercept. That is our best guess at the y-intercept. So then go with that logic, and that is technically the coefficient of B1, the coefficient of the first x, but you might know it better as what. You might know that better as the what right here. That is your best guess. Like the B1 is your best guess at beta 1, where beta 1 and B1 are both either coefficients or the true this. Like this is an estimate, which is a coefficient trying to estimate from a sample. So it's a statistic trying to estimate the parameter of the true what for the line. And so we've got this right here. Exactly, Nathan. So take this in. This is a ton of theory right here. We're going to go through it more step by step. But if you understood this right here, like, does anyone think they understand everything I've drawn right here? Because this is a good mini lecture in theory. So see how the things connect and use the color code and be like, okay, B0 is when x is equal to 0. That's the y-intercept. B1 is kind of for 1 unit change in x. It's a decent way of remembering it, but it's technically the first coefficient of the first x. And we'll see that later when we add B2, x2, which B2 will be the second coefficient of the second x. And then beta 2, x2 would be the true coefficient of the second x right there. So this is what we want to understand, a little bit of the theory behind it to know what we're doing. So here we are with the equation. These are going to be the true coefficients, not the estimates. So you see right here, we have mu y given some x, a little bit of review on the slide, and here you can see it. Beta 0, which is what we're going to estimate to be B0, and B1, which the truth for that is beta 1, is just the slope of the line. So all this right here is just review. And then we need to know, when do we do linear regression? When do we do linear regression? QQ. And what's Brian's second condition from 201? Megan, you're getting it right there. QQ. Straight enough. No outliers. So we want it to be two quantitative variables, a generally straight enough relationship, no extreme outliers. Extreme outliers bad. And then we don't want the plot to thicken. I will throw 100 points if this data started to look like this. Remember this terminology. It's on this week's assignment. If the data started to look like this, and we did this one during office hours. This could be one of your graphics for like question number 4, I think. If the data started to look like this, that is two quantitative variables. That does not have outliers. What's the issue with graphic 1, how I've created it? That is 2 quantitative variables. It's a straight enough relationship. It does not have outliers. It has heteroscedasticity. So it has a plot thickening. And what's so crazy is heteroscedasticity can be spelled with a C or a K. It's weird. It's like whatever. I don't care. People disagreed on how to spell it. Kevin remembering the other spelling right there. Heteroscedasticity. The original graphic right here displays mostly homoscedastic. Mostly, I'm a little worried. More points should indicate more scatter. Mostly homoscedastic, some minor heteroscedasticity, maybe not too much to worry about. So here are the values we're concerned about. And here's the plot thickening. Sounds so ominous. I like right there. When we interpret our intercept, and this is on the test, I cannot state this enough that this is on the test. Interpretation, fill in the blank questions, so you need to know how to interpret this. When you interpret these right here, and you know what? Let's practice. In this class, the hardest one to interpret is the slope. A lot of times, and I hate this, I want to change this for 201. It's one of the things I've said we should change. They're like, no, that's too complicated. It's not going to be the biggest thing. Is that Joe from... Is that my Joe? My Brandon? So when we have this right here, the slope interpretation is the one people make mistakes on. What we have right here, two entities that differ in by x by 1 unit are expected to differ in y by b1 units. If b1 is positive, then we would expect the one with the larger x to have a higher y. And if b1 is negative, we would expect the one with the larger x to have the lower y. So let's be very careful right here. And let's try to do this. Let's hop over to the main screen. This is where people are going to make mistakes. The intercept is very, very easy to interpret. Let's do some easy interpretations. And let's try interpreting the intercept. The intercept is the easy one. So let's go here to data. That's where people are going to lose points. I promise you this. And let's save a model. Classic. We'll predict someone's height from their weight. And let's do the intercept because it's the easiest. This is how you make a regression. I'll drop this in the chat right here. Make sure you have reg class loaded up. Make sure it looks like this also. Library reg class. And let's make a summary of the model. There we go. Easy questions. What is the value of the intercept? What is the value of the intercept estimated to be? What is B0? I'm asking the same question multiple times, and we'll just get the answer right here. The value of the intercept for this equation is what? The coefficient of the intercept is estimated to be this. B0 is this. That's correct. Great job, Alyssa, right there. Yes. B0 is this. We estimate the intercept to be this. And you can also visualize your model nice and easy, and you can see that, and it's actually off the scale. The intercept is not here. It's just that it's off the scale. So we can see where the model begins. This is not extrapolating from the model too much. But this is the estimate, and if you were to go further out, I can make it further out. I think this should... Oh, it's mad. I was doing that. Oh, because I'm doing an LM. Let me take the LM off this. Oh, really? YLim. How do I adjust that YLim? It's not YLim? Oh, and it's equal to a vector. 0 through 400. Oh, that's the YLim. I want the XLim. There we go. And then AB line. Doing this the hard way. There we go. So if you look right here, where does that about hit? I mean, I know a little hard to tell, but where does that about hit? Where does that line about hit? Where does that line about hit? This is the hard way of doing it. Takes a lot more work to do this. Where's that about hit? Looks like 55-ish, 56. And so if you visualize it, you can see that it about hits there. Now be careful. And I've had people do this. They look at this and say, no, that hits at like 60. Well, remember, what is the y-intercept? So there's important things for our interpretation. The y-intercept, which we're visualizing better right here, is when what for the line? And it'll disappear. What would you interpret for this? Think about this and think about what this means and what we're predicting right here and write an interpretation. Take a moment. This is big review. Take a moment and write in your interpretation. You are correct is when x equals 0. So how would you interpret this in context of the problem? So try to interpret this one in context of the problem. Try to interpret this in context of the problem. So take a moment. This is like a test question. Average out of a... Close. What would you say to somebody if you were talking about this? I'll tell you what I would say. Pretend you got to write a full sentence. Yeah, read right there 100 points. And then read out, add one more thing. So Reed's answer right there. Reed, top tier answer. I'm going to add a tiny bit to this Reed. There we go. Take a look in the chat right there. You'll see when weight is 0, we would predict, not that height will be this. When weight is 0, and you could say pounds, we would predict that height is 56 inches or 56.34 inches. This is illogical because people can't weigh 0 pounds. And then we could say we've extrapolated from the model probably. Will you show the code? Yeah, let me do that. You know what I'm going to do? If you are on the Discord right now, I'm in the BAS 320 general chat. Check it out. One of the great reasons to be on the Discord. If you're on the Discord, I just dropped all that code in the Discord right there. So go to the BAS 320 general chat and just grab that code right over there. It is showing on the screen, but check out the BAS 320 general chat and just say, hey, drop that code in the Discord. Probably one of the best ways for us to get code disseminated during class. But yet. So we interpreted this right here. That's the easier one. But now we got to interpret, how do you get to the general chat? It should be, Alyssa, message me if you don't see it. It should just be, if you're in the 320 Discord, you should see general chat. Yeah, Megan sees it right there. Daniel sees it. Yep, probably one of the easiest ways to get code just sent out. Love it. So I can just instantly like message everyone rather than sending. Yep, I think Alyssa found it. Great job, Alyssa, right there. Excellent work. And say, hey, Brian, drop that code in the general chat. It's easy for me to just click over there and boom, get it. Try to use the Discord more, right? Good stuff. Okay. So let's see right here. Okay, what's that slope interpretation going to be? Who would like to be in the NBA? You know, I'd like to be in the NBA. Let's write an interpretation of that slope. Don't do this. Here's where you lose points on the test, and here's where Brian sadly can't be in the NBA. He's people shorter than me in the NBA, but I'm horrible at basketball. For each 1 pound you gain, your height will increase by 0.07 inches. So you know what I should do? I should just go here and gain 100 pounds. Because if I gain 100 pounds, the model says, model's like a physical law, right? Well, I mean, while we're at it, let's just gain 300 pounds. My gosh, I'll be winning the NBA. Just winning right there. So now, 75 inches plus this. Holy mackerel, I'm going to be the best NBA player ever. What's going on right here? Brian is doing improper statistics. I'll be 8 feet tall. It's like, boom. So we're treating this model like a physical law. This is not how the slope is interpreted. Think about this. The model is saying what we expect. So that's what this red line is. It's what we expect. So 2 individuals. I'll throw 200 points if anyone can figure this out. You have to use the previous slide. But then you look at your vertical, is height the only... Good point right there, Meg. If I'm 8 feet tall, I don't got to jump. I just reach my hand up. I just hold my hands up near the rim and just drop the ball in when someone tosses. I just got to hope people can toss the ball towards my hands. So, number 1, the MVP. Points per game. 12 rebounds per game. I just go to the goal, and when someone shoots, I just like wait for it to bounce so you can't like grab it as it's going down or something. Like goaltending, what is that? I don't know. I'm not sports. So who knows how we would interpret this? Don't do this. We put no next to this. Don't do that. That is bad. You lose points. If there's 3 or 4 points on that, you might get 1 if you're lucky. If we're nice. Probably. So what is the real interpretation? I'll go away so you can see it. Here's the coefficient. Take a moment. You are super on track if you can interpret the real coefficient here. We'll see more on the slides. So you'll have notes to help you with your assignment. But what would be the actual interpretation right here? Take a moment, see if you can figure it out. This is where you want to make sure you can interpret it. See what you get if you try to interpret this. I'll give you the interpretation in a moment, but see how close you get. Where would you get? This is 4-point test question. Interpret the slope. 4 points on the test to interpret the slope. And can you do it? Can you interpret the slope? 4 points. Don't worry if you get it wrong. You'll remember getting it wrong, and you'll be like, on the test, you'll be like, wait a minute. On the class, Brian said I should add this. That might be 1.5 points max. Where is the slope? The slope is the estimate of the x coefficient. So that is the slope. Max, I'm throwing everyone 100 points. Good shot right there, Max. Good attempt at it. Don't worry, this is the one where I expect. The wording is, let's go back to the wording. Two entities that differ in x by 1 unit. So what is a 1 unit difference? Are expected to differ in y by b1 units. If b1 is positive, the entity with the larger value of x is expected to have a larger value of y. If b1 is negative, the entity with the larger value of x is expected to have a smaller value of y. It's complicated, right? Sounds like a lot. Okay, so let's check it out. Do we have any other guesses? Let's get some more points. Give it a shot. Don't worry about it. So this is where people get it wrong on the assignments and get it wrong on the test. I'm trying to save everyone some points here because I see a lot of mistakes on this on the test. And this is also useful in multiple regression. So when we do multiple regression, we'll also be doing this. So the answer, think about this. Two individuals who differ in... that sounds like cause and effect, Diego. Sounds like cause and effect. That'll only get 1 out of 4 points. Two individuals. That sounds like cause and effect, Alyssa. Two individuals who differ in their... Two individuals, because we're talking about like these points right here. Two individuals who differ in their what? It's good practice. This is when you get to the test, you say, wait a minute. Two individuals who differ in their weight. I think I'm about to copy this. I think you actually got it. Differ in their... Yep, I think Wilton's got it right there. Two individuals who differ... Two individuals who differ in weight by 1 pound would be expected to be 0.07 different in height. And then one last thing, where the person who is taller is expected to weigh more. That's got it. Two individuals who differ in weight can be expected to be separated by 0.07 inches in height for each pound different in weight. Yeah, and then just say, and the people who are taller are expected to weigh more. That would work right there, Megan. That's a little bit rewording of it, and it works. Just add on there the last part, and then the 1 pound difference is for each 1 unit difference of weight right here. So when we're saying they are differ by 1 unit, so this is where the 1 unit was obtained from, and that's where we got the 1 pound difference, because they differ in X by 1 unit. So in our example, they differ in their weight by 1 pound, and we expect them to differ in their Y. So keyword right here, expect to differ by. Exactly. Great, Nathan and everyone pointing this out. Really good practice. And just seeing this and being like, okay, how do I translate this? So you might be saying, well, wait a minute, can we do another example? And the answer is yes, because these are the tricky things where people make mistakes on the homeworks and the test. I can't tell you how many people on the test I grade these. And I'm like, no. So let's go right here and let's predict somebody's number of tattoos. So let's go here to number of tattoos. You know what I'm going to do a trick. Watch this. Attached survey 10 and numb tattoos and numb body piercings. Now this will come out as decimals probably. And let's visualize the model. We might actually get to see 0 this time. And we'll make it nicer so we can actually read it. And we do get 0. And what does it look like the intercept is very close to? What does it look like the intercept is very close to? You know what I'm actually going to switch these variables. The intercept there is very close to 0. They're not really that sloped. That's kind of a bummer. I wanted a higher slope. The intercept here is about 1.8. So if we summarize this model, we see about 1.6. So it's close-ish. What did the attach line do? That makes it so all the vectors in the data frame. Great question right there, Max. Thank you for asking. The reason I sometimes use attach is because you get the autocomplete if you're inside of here, but you see like min day Facebook. I'm always afraid I'm going to make a typo on that. So by using attach, you actually have access. Wait a minute. I should. Min, there it is. Min per day Facebook. So now the vectors, I thought it would be higher too, Megan, right? The vectors that were in the data frame are now available to be used in the global environment. Do you see how I get the autocomplete now? It attaches them to the global environment as vectors that are obtainable. So now I get the autocomplete. So if I'm worried about correctly spelling min per day Facebook, it's going to autocomplete right here, which is so much nicer than worrying. Yeah, it's so helpful to be like, just attach those. There is some issues with maybe masking. I could go into details about that. If you have things that are overlapping in what they are. Yeah, it's a really helpful little thing. Dr. Peachy's not the biggest fan of it. I like it. So that attaches the vectors from a data here. You'll sometimes, and you see now it's saying they're masked because I double attached it. If you ever have problems with attach, guess what you can do? You can detach, and now this will remove it. I think we actually need to detach twice, and now it says there's nothing there. And now if I type min per day, it's not going to appear. But if I attach it and I type min per day, it appears. So that's what attaching does, is it gives you the vectors available in the global environment. And once again, if you have things that have the same name, you could have them masking on top of each other. So if you double attach, it'll tell you that the things are double attached. There's multiple things with the same name in the global environment. Anyways, so with this right here, let's go ahead and look at the summary. You can see where the intercept is at 1.6. And so what does this mean? Now, this does sound a little bit weird, and we should probably add an average onto our interpretation of the intercept. Take a moment right here and practice. Give me that interpretation of that intercept and see if it makes sense. Here's the visualization behind to help. Remember, this is the x variable. This is the y variable. So you have y tilde x comma data equals. So what would the interpretation of this be for the intercept? Take a moment right here. Interpret that intercept. Interpret that intercept on the screen. The coefficient of the intercept is the estimate of the intercept. And then here is the estimate of the slope. So how would we interpret this estimate of the intercept? How would we interpret that? See if it makes sense to you when you say it. Like, talk through it and be like, does this make sense when I say it? Now remember, it is not a whole number, and number of piercings probably should be a whole number, but don't make it a whole number. But think about what you would say since it's not a whole number. We would expect what? Or on average, what? Pretty much, we would expect, and so Veda right there, 100 points. I'd probably give full credit for that, Veda. That's like close enough. I would just say we expect individuals with 0 tattoos to have, so it's not just one person. It'd be like an on average thing. People, great job right there, Wilton. People with 0 tattoos would be expected on average, or we predict people with 0 tattoos to have 1.64 piercings. So you didn't say will. So I think both those I would say full credit, and then some statistician's going to correct what I say too. So don't worry. Those are right on well enough that we're saying we expect people with 0 tattoos to have on average 1.64. So it's just making a prediction at 0. That's what the intercept does. But here is the confusing one where people make mistakes. You know what this means? Try to do it. Let's throw some, we just threw points. We got this. Try to interpret this slope. There's the quantity of the slope, the estimate of the x coefficient for the model. Remember, it is the x, and thus the estimate of the x coefficient. So I'll write the interpretation of the intercept here while you do that. We expect, on average, people with 0 tattoos to have, on average, a lot of on average, 1.64 body piercings. So what is going to be that slope interpretation? Here's the value of the slope. So 2 individuals, it's not always 2 individuals, but we're talking about people. So don't always say 2 individuals. Like if we're talking about bikes later on assignments, it would be 2 like different days if we're doing demands of bikes. 2 individuals who differ in their number of tattoos, correct? Because that's the X, by 1 are expected to differ in body piercings by 0.67 with a person with more is expected. Yeah. Has more, exactly. I think that's 100%. And then you didn't say the bad will word. Like sometimes I just literally, don't worry, once again, a statistician would probably say, Brian, I don't agree with you. And I'd say, well, whatever. Megan, earning everyone. Megan, this is worth 200 points. I would look at that. I would read that. And I'd say, yep. I'm throwing another 100 points on here. I can just hit the button again when it resets. But Megan, top tier answer right there. That would get you full points on the test right here. We'll try to get the full answer display. I forgot the 2 of the 2. But this would be a full points, 100-point answer right here by Megan. If you type this out right here. So this is the practice use. However, this doesn't make complete sense because you can't have half a piercing. Yeah, but this is the expected difference. Like on average, these individuals would differ by this amount. Does that make sense? So we're not saying that they will differ by this, because if you say they will differ by 0.72, then that's like what's going on, because you can't have 0.7 tattoos more. But if you say on average, people who differ by, or we would expect this difference over the long run repeated trials of observing individuals who have like zero tattoos and 1 tattoos, we would expect the average difference for these individuals, like on average, to be 0.72 number of body piercings, where the people who have more tattoos are expected to have more body piercings on average. It's a little bit of a practice. I would say this is a little practically significant. It is very statistically significant, and the statistical significance. Let me ask you a good question here. We're going to go back to the notes in a second. I'm going to get. Oh, yeah, that's a quote. I tell you, 320's got the jokes and the quotes. I love it right there. Putting that in. Okay. So let me ask you this. Which of these looks like how we should denote significance? Do you think where the slope is at, which is my elbow, or do you think the intercept, which is where my elbow is at, or do you think the slope would denote significance? Do we want to see if the intercept is equal to 0 or the slope is equal to 0? Which of these would denote significance? Like if we have a slope that's not equal to 0 or an intercept that's not equal to 0, which of these would be a significant line, a relationship between x and y? Which of these do you think we should look at here? The p-value of the intercept, which would tell us, oh, that intercept is not equal to 0. Ooh, that's strong evidence the intercept is not equal to 0. Or we want to look at a slope and see, because the slope is the xy relationship, right? Sorry, intercept. No one cares about you. This p-value right here for the intercept, you know it's coming. It doesn't matter. That p-value doesn't matter for the intercept. I don't check significance of intercept. Cool. The intercept's not 0. What do we care about? We care about the XY relationship. And what is the XY relationship? The XY relationship, being statistically significant, is the significance of the what? We're understanding how to read this output right now, which is very important. The XY significance is the significance of the what? What variable is this? It's the variable that creates the what of the line. The XY significance, the significance of the line, is the slope. And guess what? The significance of the slope is the significance of the model. Do you see how these two numbers here are identical? Because this is the full model. This will come into use more in multiple regression. But the significance of the model itself is the significance of the slope. It doesn't matter. It doesn't matter what the intercept statistical significance is. What does a p-value of an intercept even do? The chance of the it tests right here to see if the intercept is equal to 0. So the mathematical test for this would be, I'll draw it out real quick. Both of these have a very similar mathematical test. And the mathematical test for the intercept would be, if we were to solve it by hand, we would take the value of the intercept, compare it to 0, and divide it by the uncertainty in the intercept. And this right here, if you solve it, is really just taking your intercept and dividing it by the uncertainty. And this is important. We've covered a lot right here with this output. Does anyone know mathematically what this solves to? If you divide 1.64 by 0.08, what do you get? If you take basically your estimate and divide it by the uncertainty, because you don't have to subtract the 0, it's just a 0. If you divide these two numbers, guess what you get? Has anyone solved that mathematically? I can solve it in my head. You get the t-value. which is that'll get the t-value. So that gets you the t-value. And from the t-score, what do you think we then solve? So it goes in order. From the t-score, we then solve for the p-value right here. So this would get you the t-score of about 20.5 or so. It's up there, full notation, if you want to see exactly what it is. What we then do is we plot this value on the associated t-curve, and the t-curve really only goes out in most instances, like a normal curve, out to 3 and -3. So where would the value of positive 20.5 be on this curve? The t-value is a standardized version of our estimate. So good questions right there, Nathan. The t-value is a standardized version of our estimate, telling us right there, way to the right, it's off this scale. So do you think if we went way off this scale, like really, really far off the scale, how much area do you think would be outside of it? How much area do you think would be outside of it? Because we're just like completely off the scale. So there's no area outside of it, telling us that this intercept is probably not 0. All of this work right here just to see, is the intercept equal to 0? And the answer is, even though it looks close to it, yeah, the intercept's probably not 0. So what do you think we test when we test the slope? And this is why it's more important here. When we test the slope, the equations are virtually identical. This time, we're just going to test to see if the slope is equal to 0. So we're seeing right here, is the slope equal to 0? So how do you mathematically do this? Well, you would take the value of the slope and divide by the uncertainty. And just look at it. It actually looks kind of nice. Almost it's like 7 divided by 1. So if you did 0.73 divided by 0.11, you should get about this right here. I mean, just carry your decimals a little bit more than I did, but you'll get this right here. But once again, when we do this, where do we fall on the curve? Where do we fall on the t-curve? And this is all done for us. Where do we fall on the t-curve? We fall where on it? By getting a value of like 6.56. We get a value of what? It's basically none again. Does that make sense? We're way off to the right here. We're like, okay, this is off the curve, and that means it's statistically significant that it's not likely to happen. Now, what values of slope would be likely by random chance? What values of slope would be more likely by random chance? Who knows a value of a slope that would be more likely? That one's all right. That one's, yeah, that's great. What values of slope would be more likely by random chance? And that's a good example. Like it. So the p-value of the slope will show you how likely it is that you got on the slope. Exactly. Wow, Max, great answers. Max, that's perfect. Yeah, the p-value tells us the likelihood of our slope given the true slope is 0. That's exact classical statistical way of wording it. Max, I just hit that 100-point button immediately. Max said, so the p-value of the slope will show you how likely it is that you would have gotten that slope or a slope more extreme given the true slope is 0. So if that helps with your statistical wording of it, Max, that's exactly correct. And look at this. The slope we observe here is what given the true slope is 0. The slope we observe here is what given the true slope is 0. Just think the p-value is high. So this slope we observed right here was very what given the true slope is 0. Max, that's worth another 100 points. Max, great answer. Better than my answers. So this slope right here looks very what given the true slope is 0. It looks very likely. Like there's no slope. So this is what I should see if the slope is 0. And the slope was found to be this value right here. And then what do we do to get the t-statistic? We divide by the standard error. So if you take this number right here and divide by the standard error, you will get the t-statistic. And the t-statistic is just a standardized version of your slope. Now, what you would then go and do, which we don't do, is you would go over here to the t-applet, which I think I do have MuBot having a quick link to. MuBot will send us over to the t-applet right here. We would not do this by hand, but this is calculated for us. We're thinking about the probability of a slope as extreme or more extreme than our slope, and the value we just obtained was negative, this right here. And truthfully, it doesn't matter if it's positive or negative, because it's going to do both sides. And then the degrees of freedom, I think, was 697, which we don't calculate for this class. And look at the p-value, 0.771. And this is the same value we are seeing in R right here, a little bit rounded right here. And R might be carrying more decimals in the background, but 0.77, and there's 0.77. And remember, for the previous examples, our t-statistics were very high. And this is a great note to have. If your t-statistic is higher, what happens to your p-value? When your t-statistic is higher, what happens to the p-value? For higher t-statistics, your p-values will be water. For higher t-statistics, your p-values will be water. For higher t-statistics, your p-values will be water. The higher the t-value, the lower the p-values, because these were less likely by random chance, because the only way to get this is to have a higher coefficient right here. And it's a coefficient to uncertainty ratio. So we want to have a large coefficient, but a small amount of uncertainty. So is that higher in magnitude? Exactly. Max, top tier answers today. Yes, Max. Great answers. It wouldn't matter. Rockstar already said that about 10 times today. If it was -1 or +1, it wouldn't matter, because all this would do, especially if we are reviewing, this is a good review right here. If this were to be a positive t-statistic, it would be the same. Sorry, buddy. If this were to be a positive t-statistic, it would only change the what of the correlation. If this were to be a positive t-statistic, then the estimate would have to be positive. It would only change the what of the correlation, or the slope of the regression, which is the correlation and the slope of the regression will follow each other. It would change the sign, so it would just change the direction. Great answers. It would just change the slope, the sign, the direction. And so it wouldn't matter. It would still be the same uncertainty. Because think about this. A slope like this is just as possible as a slope in the negative direction. The most likely slope, if there is no relationship, is a slope of 0. Now, when you look at something like this right here, you can quickly tell via the visualization that this looks basically impossible given that there is no slope. And that's why we see ridiculously low p-values and very high t-statistics, and knowing this right here. And I do want to state this again, and we've almost talked through his whole output. What did Brian call the standard error? Brian has called repeatedly the standard error this, and this is going to be a theme for the class. Did anyone catch the word whenever I said this is your what in an estimate? And it could be your standard error for your slope, or your standard error for your intercept, or many other times through statistics we'll use standard errors. It's just your unwhat in that estimate. You can say like, well, I estimate the intercept to be this, but then this is my amount of this in it. It's your what. The standard error is your uncertainty. And watch this. If we were to go up and down 2 uncertainties from this, and this is later, we're going to hop back to the notes. Do you see this? What did Brian just make for his slope? And this has been on the test too. Brian just estimated, and look how close that number is to this and to this. I went up and down 2 uncertainties. Brian just made a what for his slope. By saying, well, let me go this amount of uncertainty above and this amount of uncertainty below. I went out 2 uncertainties. So I just made a what for my slope. Confidence interval. I just built a 95% confidence interval. And if you want to go more exact, you can go to classical statistics with 1.96, and you'll get even better estimates that are even closer to what it's going to give you had you not just let the computer do it for you. And you can see my numbers now are much, much closer, but it's doing all the fine estimates for me using 1.96. We don't have to do it all by hand, but we should understand the theory, and that's what we're getting for. So what are the standard errors? Standard errors are just uncertainties in estimates. If I tell you I'm going to arrive to your house at 5 p.m., it is coming back full circle, right? If I say I'm going to arrive to your house at 5 p.m., and then I say, but I could be off by about 10 minutes, what is the uncertainty? So this is saying, I think the slope is this, but I could be off by about this much in my guess of it. Because this is just a guess of the slope. I'm just saying, I think the slope is this, but I could be off in about this much. If I say I'm going to arrive to your house at 5, but I could be off by about 10 minutes, the uncertainty is 10 minutes. Now, does that mean I can't arrive at 5:11? If I arrive at 5:11, you're like, no, you said you'll be here about 10 minutes off. I'd say, well, about 10 minutes. Exactly. So this is just a guess of the uncertainty. It's like, well, we could be off by about this amount. So I'm saying I'll get there at 5, but I might be about 10 minutes off by that estimate. It's not saying I am 10 minutes off. It's just like a degree of uncertainty by which we could be off, which this is right here. I think the true coefficient is 5, but I could be off by this amount. Just talk about it that way. And then you could say, relative to my estimate, there's very little uncertainty because the t-statistic is high, which implies there's very large statistical significance. Huge mega review. Let's hop back into the notes. Reading your output is very important. And if you notice now, we're just interpreting these coefficients right here. Now, if you notice earlier on, we can actually do more than 1 unit of the slope. You could actually time the slope coefficient by 3 to talk about 3 units. When Brian did his weight for basketball, he actually looked at an increase of 300 units in weight and then said we would expect Brian to be 21 inches taller. The correct interpretation of that problem would have been 2 individuals who differ by 300 pounds, I think it was, are expected to differ in their height by 22 inches. Does that kind of make sense in your world? If I say 2 people who differ by 300 pounds are expected to differ in their height by 22 inches, where the person who weighs more is expected to be taller. Does that kind of make sense? Or if I said 2 individuals who differ in their weight by 100 pounds are expected to differ in their height by 7 inches, where the person who is taller, this person who weighs more, is expected to be taller. So once again, listen to that 100-pound difference. If we have an equation right here, which I'll write down so you can see it, where we are predicting somebody's height, and we have right here that 54 is when people have a weight equal to 0, which is an extrapolation of the model. And then we go right here and we say 0.7, and then we have weight. This would be for 1 unit. 2 individuals who differ in their weight by 1 pound are expected to differ in their height by 0.7 inches, where the person, it should be 0.07. Too big of units. 2 individuals who differ in their weight by 1 pound are expected to differ in their height by 0.07 inches, where the person who weighs more is expected to be taller. But if you times this by 100 right here, then we would be saying 2 individuals who differ in their weight by 100 pounds are expected to differ in their height by 7 inches, where the person who weighs 100 pounds more is expected to be 7 inches taller. Does that make sense? Would you expect that? Like if someone weighs 100 pounds more, you'd say, well, I'd expect those people to be about 7 inches taller if they weigh 100 pounds more. Does that make sense? It does. Awesome right there. And do you know what we don't say? We do not say, if you gain 100 pounds, you will get 7 inches taller. It's not what we say right there. Don't say that. That's where you lose points. So there's a lot of bad ways to say it. And we have all the interpretations right here to practice. We did a bunch of interpretations to practice, but when you are doing your test questions, make sure to reference this. We did a few interpretations. I just like doing our own because you can always review the notes, and I never like reading the notes verbatim. But notice right here, this is not 2 individuals. This is 2 bills at a restaurant. 2 bills at a restaurant that differ in their bill amount by $1 are expected to differ in their tip percentage by 0.23, where the higher bills are expected to have lower tips. So it's all proportional, and if X is off by a factor of some amount, will we anticipate Y to be off by the... Exactly. If you do like 100 increased unit of X, it'll be 100 increased units of Y. Does that, Nathan, great answer right there. So usually we just do the 1 unit because you can just do the basic 1 unit. But if you go up like 5 units of X, then you'd expect a 5-unit difference of Y between the individuals. So right here, I could say 2 parties that differ in their party size by 10 people are expected to differ in their tip percentage by how much? 2 parties that differ in their party size by 10 people would be expected to differ in their tip percentage by how much? So 2 parties, which kind of really goes beyond the model, that differ in their party size by 10 people. We generally, use the 1 unit. Don't go, 9.2, because then you would just times this by 9.2. And unless we ask you to, which we don't always, usually go with the 1 unit, which is on the slide, where we'd say 2 parties that differ by 1 person in their party are expected to differ in their tip percentage by 0.92, where a larger party is expected to have smaller tips because of the negative coefficient. And then this is illogical for the intercept because there can't be a party with no people in it. Exactly, Veda adding in that extra right there. Great job, Veda. And then be careful for your meaningless intercepts. A lot of people say, well, how do you know if an intercept is meaningless? Here, wait, just listen to me, ready? This is how you know. For parties that have no one in them, that's meaningless. Just pause when you do your interpretation and say, does this make sense? For a bill of 0, I actually, as a waiter, have given bills of 0 as a joke and got a very good tip. So I actually might dispute that one. I did give someone a bill for waters and they gave me a tip. So I might dispute that. For someone with no experience at a company, for individuals that have no experience. So, hey, this is meaningful. This one is definitely meaningful. Among individuals that have no experience on the company, we would predict for them to have a monthly salary of $3,526. So if you ever wonder, is something meaningless, just pause as you're saying it and say, for individuals that have no education post-high school, so it's 0 years of education post-high school, that makes sense. We would expect their salary to be $3,229. Now, if the salary was negative, that would also be meaningless, but the model makes sense right here. Like we're saying makes sense. It doesn't sound meaningless. If you run into something meaningless, you'll usually say something like, when there is nobody in the party or for a party of size 0, we would expect the tip percentage to be 18.4. And that's when you're like, that kind of sounds meaningless. It kind of sounds like model wouldn't do that. When there are no renting households in this census block, we would expect the what? We would expect a what response rate. So a pause right here. Take a moment. 50-point question. When there are no renting households in this census block, we would expect a response rate of what? When renting households are equal to 0, when there's no renting households, we would expect a response rate on this census to be what? When there are no renting households, we'd expect a response rate on the census to be what? On average. And I would visually look at it. Great job right there. Nice job. Excellent work. Yep. And does that make sense? That's logical. It's like, okay, then no one rents. It's just like, well, can renting household equal 0? Yeah, there's no one renting. It's the amount of people renting. So if it's equal to 0, we would expect this. Makes sense. 2 census blocks that differ in the fraction of renting households by 1% are expected to differ in the response rate by 0.25, where the people who rent more, the more renting, are expected to have lower response rates. If you worked for the census, what would this tell you? You would say, okay, we have to put more efforts into areas where people rent. So this kind of makes sense that this would be what's significant. It's probably statistically significant. I've looked at a lot of data. I'll tell you that's statistically significant. I've seen enough data. So with this right here, we could run the model if you really want, but I promise it is. But Brian's saying we're going to have to concentrate some efforts in these areas because we're getting much lower response rates on average than the lower renting. So we're going to have to put more effort into this. This looks like we're going to make decisions from this. This definitely looks to be what to Brian? Because it's a decent enough slope that if we have a difference of like 10%, we're going to see a lower response rate expected of about 2.5%. And also the model goes up to like 80%. So we're seeing around a 20% difference. So between these two areas, we'd expect right here, between here and here, around a 20% difference. The 20% difference is being obtained by timesing this by the 80 units, just to obtain the expected difference between them. So I'd say a 20% difference in response rate out of 100%, that's what that difference is, sounds very what to Brian. I'm making arguments for, we're going to make decisions from this. This sounds what significant to me. So you always have to argue this one. This is not the yes, no. This is not the p-value. This is the what significance. So the significance you argue for, and you have to make a case for, that Pepsi was like, we need to know why this matters. What decisions are we going to make from this? And I'm going to say we're going to have to put more effort into these renting blocks. Where people are renting, we're sending more people, spending more time, practical significance. Great job right there, Nathan and Wilton. We're going to talk about the practical significance right here. And let's start up the least squares. We've done a lot of work today to prepare ourselves. We will be doing activity later tonight. Swing by, answer those questions. Gives me all that energy. You got it. So when we do this, we mentioned this earlier, we're going to pick what line. Who knows what line we're going to pick? Because we can pick any line. Let's just pick that line. This is a line. Line. What line are we going to pick? What line are we going to pick? We don't want any of these lines. We want that line that fits through the data the best. And so what is the line that is going to fit through the data the best going to do? The line that fits through the data the best is going to reduce the sum of the squared error. Now, when you hear error, what we call error in statistics, and we were doing this during office hours today, is actually a residual. And remember residual wrap. Residual E is the actual point Y minus the predicted value, and the predicted is y hat, and this is the residual. So a residual is your actual minus predicted. Anything above the line will have a what residual. Anything above the line will have a what residual. So any point above the line will have a what residual. Any point that is above the line would have a what residual. It would have a positive because it's above the line. If you were to take the actual value over here for this y, subtract it from the line itself, you're going to get a positive value because it's above. It's like higher than the line of prediction. Anything below the line has a negative residual, and anything on the line, the actual would be the predicted, thus it would have no residual. Just think about residual like left over if there's something residual. So what do we get from our predictions? We have our residual, things that are not explained. These are not good. And what we'll be doing is taking every residual and finding the sum of the squared error. Remember what I said a second ago? The actual minus predicted is the residual, y minus y hat, so that is just the residual. So when we do this right here, what we're actually visually doing, I think we showed it on the other slide. Check this out. To find the sum of the squared error, we are literally doing this. We're literally going right here and taking this error and squaring it. Taking this error and squaring it. Taking this error and squaring it. Square it, and oh no, it's not that bad. The other one's bigger. And then what do we do to all these squares we just made? So we take the error, square it, and then what do we do to it? Add them up. Great job, Alyssa, right there. Why not just add the residuals? Like, let's just add the residuals instead. Like, this residual here is like -3. This is +4. This is -3. This is 2. I didn't do the math properly. This is -1. Here we go. This is -4. Pretending. And close. And then that. And then this is +4 also. Good. Why not just, yeah, exactly, Max. I was trying to do the math and my brain just couldn't math at the moment. That's -1 right there. And you're going to see that they're going to cancel out because that's what the line of best fit does. So by squaring them all, if you go in here and square them all, instead of these being 4, you'll get 16. And then down here on the bottom, you get 16, 9, and 1. We're just making estimates. We were not meant to find these. But we're just showing that by squaring them and then summing them, we're going to find out exactly. And the theory here is pretty important. It's like, well, why are we squaring it? Because if we just take the error, then they cancel each other out because the line goes through the points. So we'll square them, and then we'll add them up to find the total amount of error. We don't want there to be error. What would be a really good sums of squared error? Does anyone know the best sum of squared error to get? I'll draw it for you. The best, you got it, Nathan. Great job, Nathan. Excellent work today. The best sums of squared error to get would be 0, and that's when there's no residuals. Everything would be on the line of prediction. And the worst sums of squared error to get would be something where the line is completely flat. And we'll have a special name for that called the naive model. And this is when the slope is equal to what? I got it decently, but this right here is a horrible sums of squared error called the naive model, or if this is our regression model, then it's basically the naive model. And we can always fit the naive model to ours. We'll end here in a second because I don't want to hit another topic probably. I could fit the naive model, and then I could calculate the error from the naive model. And this would be our baseline error for what we have. And I think we might end here because I don't want to hit another topic with so little time left. So we can calculate the sums of squared error from our model or the naive model. This is the naive model. And my last question of the day, the naive model is the what of y. Last question, getting us ready for next class. Here's our models. This is the regression model drawn on it. And the naive model, last question, 100-point question of the day. The naive model is the what of y because it doesn't use x. The naive model, which I've drawn in there, a lot of info on this slide right now. The naive model is just the what of y. Close. What does y bar mean? And think where it's at. The naive model, not quite the y-intercept. Max right there, 100 points, the mean of y. That is the mean of y. The naive model will be the mean of y, and we're going to go more in depth on this next class. The naive model is the mean of y. So make sure to write that down right there. Naive model is the mean of y. That's got it. Great job, everybody. I know there's a lot of topics. It's going to come down to some practice. We're going to be reviewing tonight. So swing by. Let me get that video up and going. I need to make it later. I'll send out an announcement on Discord and all that great stuff. And thank you for those asking. You know what we'll do? No, we do? Drop this in the Discord real quick, right? What happens if I do this? Tell me good idea, bad idea. Oh, wait. I'm going to drop all this code in the Discord right here. Does it all drop? Wow. Associated own attractiveness height survey 10. Pretty neat. Oh my gosh. What? Like right there. Dana says what? Let's look at this. The association between... I'm interested in this. I'm throwing 100 points right there for James dropping in some code. It is so someone's height and their own attractiveness. Probably the thing about this. Here, we'll go to the main screen. What do you think is the deal with people's height? And we could look at the model for this. There is a model for explaining people's attractiveness based on their height, and it is statistically significant. So there is a relationship to taller people thinking they're more attractive. But what do you think it might be? I'll tell you the way to handle this pretty quickly. What do you think might be the lurking variable for why people who are taller might think they're more attractive? We could see if it's the lurking variable. This is not meant to cover extra topics right now, but it's a good way we can check very quickly to see if it might be gender. Yep. You know how you can check that really quickly? If you ever want to see if something is a lurking variable, you add that variable to the model. This is hints for multiple regression. You simply add that variable and take a look. What do you notice is statistically significant now, but what is not statistically significant? So take a look. The real differences on why people think they are more attractive, and here I'll visualize it. There's the visual for it. The real difference why people think they are more attractive is actually what? Here's what's statistically significant in this model. Here is the previous model where height was significant. In the new model, height is not significant. Only this variable is statistically significant. And you can see the differences where we have a line for males and we have a line for females. And there is a little bit of a slope to this still. But the real significance right here looks to be really that people's own attractiveness is probably best explained, like how attractive they think they are, is probably best explained by their what? Wow, that's attractive out of 100. So this would be two individuals where one is male and one is female, but are identical in their height. The individual who is male is expected to rank themselves about 4.55 points higher than the individual who is female. We have not gotten into multiple or categorical, but this is an idea of lurking variables right here, that it was actually gender. And I'm even wondering if there's an interaction right here, which is definitely multiple weeks away. Oh, there is an interaction. Oh, that is so cool. And the interaction, I'm throwing 100 points. This is really, really fascinating. And it goes with something I might have guessed. The relationship for how females see their own attractiveness is what to height. That is so crazy. The relationship to how females see their own attractiveness is what to height. Wow. The relationship with how females see their own attractiveness is negatively related to height. Does that make sense? The female line is the black line right here, and two individuals who are female are expected to differ in their rating of their own attractiveness. This is way more complicated to do right here. Where the individual, here's the slope for females, where the individual who is 1 inch taller is expected to rate themselves about 0.2 points lower on average for their attractiveness rating. Where two individuals who are male, now we need to get the slope for male. The slope for male is going to be following. Two individuals who are male, that's the slope for the male line. We're like a month ahead if we're looking at this. But two individuals who are male are expected to differ in their ratings of own attractiveness when they differ by 1 inch in their height by 0.78. That's the slope of the male line, where the individual who is male and taller is expected to rate themselves more attractive. And so there's an interaction here. This is such a cool example. but there's an interaction here on the way in which height is associated with somebody's rating of attractiveness, where it's dependent on someone's gender, where females who are taller actually have a negative relationship with how they view their own attractiveness and height, but males have a stronger relationship with how they view their own attractiveness and their height. Wow, that is such a cool example. And I wonder if there's like there's so many things to look at. This was an amazing example. But here's the thing. Is this that practically significant? Oh my gosh, I will throw someone 300 points if you point me to the right value to say, well, Brian, this was all fun and cool, but there's not much practical significance to this. If you look at the scatter of the points, that indicates something because there's a lot of variation. This is statistically significant. The p-values are just barely there on some variables. But the practical significance is really missing. And where should you go? Did I say 300 points? Does anyone know? I don't know if anyone's even watching anymore. Where would we go for the practical significance? Because I don't think it's really there. Although we do see some sort of relationships right here, the whole relationship itself is not really that strong, not useful. Close with the F. I'll take that. Let's throw 300 points. Mun, thank you for, that's a good guess right there. The F statistic, you could kind of interpret it. The variation we see explained versus what we would expect due to random chance is about 8 times more. I would go here to the R squared. We're only explaining about 3% or 3.3% of the variation in people's attractiveness based on their height, their gender, and the interaction between those variables. That only explains about 3.3% of the variation, which is not much. There's a lot of the variation left unexplained. And in truth, probably a better variable might be something like weight. If we were to throw in here weight, we might actually get it better. Is it weight? Does weight explain people's attractiveness? No, it's just as good as height about. It's only about 3%. Yeah. So there you go. We don't really have a significant model. I mean, the model is significant, but we don't have a practically significant model. And weirdly enough, the weight doesn't come back significant on the only on the main effect, on the main variable. That was cool. I love looking at data. I love seeing what we see. And that's got it. Good stuff, Mun. Here's another 100 points. Thanks for hanging out to the end here, Mun. Remember, the R squared is practical significance. That's a good note to take. Lot going on the screen, topics we haven't covered yet, but the R squared right here is the practical significance on do I care. There's only one statistically significant thing. This model is actually statistically significant, probably because of the variance inflation. Yeah, it's variance inflation. R squared is practical significance. Mun, that's worth another 100 points. Thank you for repeating that. Good practice right there. R squared is practical significance. We covered a lot of different topics right here, which we'll be getting into later in the semester, like variance inflation, interactions, indicator variables. This is a lot of different chapters that are building upon what we did today. If you look at the output right here, it looks very similar to what we were doing earlier on. Look at this output. We did this today. And then look at this output. Looks virtually identical, but with more variables. So we've been building the backbone of our knowledge today, and we'll be doing that next class here on Stats 201 BAS 320. Bye for now, everyone. Bye!